Okay, hey guys, I will be explaining Codeforces round 886 Div 4 that just ended yesterday, and I will be explaining all the problems from A to H. So let's get started. So for the first problem, I think this is just very straightforward. You're given three digits, and you want to check if you can choose any two digits to make the sum greater than or equal to 10. Um, there are um, quite a lot of approaches to do here because the first thing is that there are only three digits, so you can pretty much just case bash. Um, but there are like obviously faster ways to implement this problem. So the first solution and what I did was I stored the three digits in an array and then I sorted them and then I checked if the last two digits have a sum greater than or equal to 10. If they do, then the answer is yes. If they don't, no, because those two digits will produce the highest possible sum of any two digits. So if the highest possible sum is not greater than or equal to 10, then any other sum will not be greater than or equal to 10. And that's exactly what I did. Um, so I started in an array of three elements and sorted them and determined whether the sum of the last two digits will be greater than or equal to 10. I also read the editorial, and what they did was instead of doing all of that, we can just check the sum a plus b plus c and then subtract it by the minimum of these three. Because this will be the sum of the largest two digits among a, b, and c. Because this is the minimum, and if you take away the minimum from this sum, it's just the two that are highest. Okay, let's go to the next problem, letter B. This problem, you're given n participants, and each participant has a response of AI words long and a quality B sub I. Um, and the no two response of the same quality, at least one has a length of at most 10. Uh, we have to determine what is the which response has the highest quality but has uh, has not or such that the response is less than or equal to 10 words, and that response always exists given this condition, so we have to find that. And since there are no two responses that are equal or have the same quality, and that means there's only one winner in this problem. So how do we solve this? Well, this just is straightforward like maximum problem. But the catch is that you only consider those responses that has length of at most 10 and update the maximum quality and update um, the index of that participant. I also did another way to implement this, which I think is slightly more straightforward during contest. What I did was I stored it in a uh, three length array, or no, sorry, I stored an array of tuples given each tuple contains the quality, then the words, or the length of the words, and then um, the index of that participant. Then I sorted it and um, we go from left to right and find the first instance such that the response length has at most 10, and that will be the answer because I sorted it in non-decreasing order. That's exactly what I did. So I stored the participants' information in terms of their quality first, then the length of the word and their index, and then I sorted it in non-decreasing order, or no, sorry, non-increasing order, and then find the first one that satisfies that the length of the response is at most 10, and print out the index of that response. Okay, and the third problem, word on the paper. I think, in my opinion, this was the easiest. I think this problem was like the fastest that I got the insight on. Basically, you're given an 8 by 8 grid of dots, and there exists a word that is written vertically in one column from top to bottom. So what is it? So these are some examples, and this is just an implementation problem. You want to go from, for example here, from top to bottom, and from left to right or right to left doesn't matter, but left to right is more convenient. Once you hit a word, and since you're going from top to bottom and it only goes vertically, then the first time you hit a letter is the first letter in that word. So you go downwards from that point. You only stop when you hit a dot after going down, or you hit a cell that is out of bounds. So, for example, after E, you will hit an out of bounds cell, or for example, this one, A, you're already in the boundary, so there's no more cell after that. And that's exactly what I did. So I stored the grid in an 8 by 8 array of characters, and then we traverse from top to bottom. The first time that the character in that cell is not a dot, we go from that cell down until either the cell is now out of bounds or the cell is a dot, basically, and print out the word. And the important part about this problem is that you should stop your traversal once you found uh, the word, because if you're going from top to bottom, let's say you finished printing lost, then you will traverse. If you don't stop, you'll traverse, you will continually traverse and hit O again, that algorithm. So you will be reprinting OST and then ST and then T. So you don't want to do that, so you have to stop after printing the word. Alright, so now we'll go over more interesting problems. And it starts, in my opinion, from problem D. So problem D, you're given n problems, and each problem, or problem I, has a difficulty a sub I. You will do the following process. You remove some problems from the list. You can also not remove anything. And then you rearrange the problems in any order. And then we define a round to be balanced if the absolute difference between the difficulty of any two consecutive problems is at most k, less than or equal to k. And you have to find what is the minimum number of problems you have to remove so that that an arrangement of the problems is balanced. So for this problem, this is an observation problem, and the observation is that consider a problem. Like, let's fix a problem. Let's ask the question: what are the problems that um, gives the least absolute difference between it and the problem. Because if you minimize the absolute this difference of the two consecutive problems, then it's more likely to be at most k, if that makes sense. But luckily, the closest like difficulty for a certain problem is are the problems that if you plot them in a number line are the closest towards the left and towards the right, if that makes sense. So for example, for the closest problems or the closest problems or the closest difficulty would be 2 and 5, and it just means that yeah, and we can achieve that by sorting the array in some order, um, non-decreasing or non-increasing. It doesn't matter. And as you can see, if we sorted them, you will be achieving the for each problem, it will be consecutive to the to and from uh, the closest problems with or with the problems with the closest difficulty. If that makes sense. So the key idea is that you have to sort the array a sub I, and in that way you will have the most chance for a problem to be included in the end. Now, suppose that we sorted a sub I, or the array A, and we found two problems that are consecutive or that are adjacent, such that their difference is greater than k. So the difference is greater than k. There are two cases. Um, you only consider this array or this array, because if you this guy cannot, or this element cannot be adjacent to this element because they have a difference of at most k, but neither those elements towards the left, because they have at least the same distance or difference between this and this, and similarly in this case. And that means that either this would be the subarray, or you will find a closer pair that also does not satisfy the condition, which means our answer will only be the number of elements, or the maximum number of elements in a subarray whose adjacent elements have an absolute difference of at most k. So you have to find a subarray such that in that subarray a sub j minus a sub j minus 1, and we have to take the absolute value, is less than or equal to k. For j from, let's say, L plus 1 up to R, and the subarray is a L up to R. Right? And we can implement this using double while loops or whatever implementation. You can do it in a single for loop, and then you can just reset the counter with some stuff like that. So that's how this is how I implemented it. I sorted the array A, and then I iterated from left to right, and then each iteration I will greedily take the next element as long as its difference from its previous is less than or equal to k and it's not out of bounds. And notice that j here is actually the length of the subarray, so we will update our answer to be the maximum of the previous answer and j. And then after that we will go towards the next unconsidered element or out of bounds. Actually, the answer is not the maximum length of a subarray with consecutive elements to have a difference of almost k. It's actually n minus the length, because um, you want to minimize the number of problems you need to take out. So you want to maximize the number of problems that would be left. Okay, so that's problem D. And then problem E. Basically, you're given n pictures, and each picture is a square with the side length of s sub I. So for the ith picture. And for each picture, you will be mounting it on a square piece of cardboard such that um, there is a border of W on all sides of that picture. And in total, he used c square centimeters. So note that this is not the border is not the only cardboard that is used. It's the whole square. So there's a cardboard behind this blue square, and cardboard behind this red square and yellow square. Given the picture sizes and value c, can you find the value of W? So I read the editorial, and there are two ways to solve this. During contest, I solved it using math. Maybe there's other ways, but there are two main ways to solve this. I solved it using quadratic formula, while the editorial mainly solved it using binary search. And the reason why binary search works is because suppose W, like our current W, doesn't work, right? So we check some W, it doesn't work. Then all of the W's that are greater than this W will also not work, because, or sorry, if this W didn't work, and let's say the value of, like, supposedly C that we used or that we computed is greater than C, then all of the W's that are greater than this current W will not work. Similarly, if we consider a W and the total cardboard computed is less than C, then all of the W's that are less than this W will not work. So there are only and that means that we can use binary search. And there's only one value of W, I think, that could work. So that also makes sense. Okay, so that's the idea for binary search. So you just want to compute the summation from I equals 1 up to n of s sub I plus W squared, where W is the variable that you are iterating between, say, L equals 0, or is it 0? Yeah, L equals 1 and R equals 10 to the 18. But that's not what I did. I did some maths. So this is what we want to find, right? So this is the summation that we want to find, and it follows that C is equal to this summation. So let's expand this summation. So this is the summation from I equals 1 up to n of s sub I plus 2 w s sub I plus w squared, and then we sort of distribute the summation. So it's just the summation of s sub i's plus 2 times w times the summation of, or no, sorry, this is si squared and this is si squared, summation from I equals 1 up to n of s sub I plus, since there are n elements here and this is a constant, if you distributed this will become nw squared. Now let's suppose, or let's let this to be A and this to be B. So our equation now becomes A plus 2bw plus w squared equals C, or in other words, w squared plus 2bw plus A minus C is equal to 0. And notice that this is the only variable that we have because B can be computed, A can be computed, and C is given. So W is our only variable here, so we can simply compute W. So W will just be negative 2B plus, the reason why we're only considering the positive square root is because if this becomes negative, we know that b is positive, so negative 2b is negative. So if this becomes negative, the whole numerator becomes negative, and the denominator is positive. Okay, wait, actually there's nw squared here, I kind of forgot. The denominator is 2n, and this is positive, so w will become negative if you use negative sign. So you will only use the positive square root. So this is square root of 4b squared minus 4n times a minus c all over 2n. So this is the answer. And since w is guaranteed to exist and is an integer, then the only thing that you have to worry about is the squareness of this inside expression. And since w exists, you know that this is a square. So if you, I think in C++ and in Python, if you take the square root of a square number, it will precisely give you the square root integer. So there's no need to worry about precision. I think, correct me if I'm wrong, but the only thing that you have to worry about is overflows, especially in C++, because I'm not sure if this right here is, this value here can be contained in or stored in a long or 64-bit integer. I'm not sure, but yeah. So because of that, I actually coded this in Python. This was my first code, but then I realized this might be too big right here, so I coded it in Python. And that's pretty much the value. Actually, whoops, this is actually wrong. This should be 2w. So we just divide it by 2. We divide it by 2 actually. Yeah. So the answer should be, yeah. So there should be 2 here. I kind of forgot about that. Okay, so that is problem E. And then for problem F, you have n frogs, and then each frog only hops AI units forward, and you can place a trap, only one trap on the first n points, and you want to find the maximum number of frogs that you can catch using that trap that you placed. And it is dependent on where you placed it in the first n points. And then you cannot point it, or you cannot place it in point 0, obviously, because you just catch everyone. Okay, and then how do we solve this? So the problem here is that a sub i's are can be duplicated. So for example, here three, there are two threes here, and then here we have two threes here again, which means the if you do it one by one, you cannot achieve the harmonic series time complexity. Um, because the key idea here is that you only need to consider the first endpoints, which is up to 2 times 10 to the 5. So you can do the harmonic series time complexity, which is O of the floor of n over 1 plus the floor of n over 2 plus dot 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 up to the floor of n over n. Because notice that if a sub I if a sub I exceeds n, then it obviously won't be catched, so you don't have to consider that value. And the reason why this is fast enough is because this is approximately, or not approximately, but it is equal to n log n. And I think the reason for this is because when you consider, obviously this sequence right here is greater than this sequence or series here. So let's quickly list it down. And consider the series n over 1 plus n over 2 plus n over 2 plus n over 4 plus n over 4 plus n over 4 plus n over 4, and so on and so forth. And notice that um, I don't know, let's say 2 n or log base 2n. Consider these two series and notice that this series is actually greater than or equal to this series. But we can prove that this is like n log n. So this is equal to n times 1 plus like 2 times 1 half. So it's like 1 plus 1 plus dot dot dot. Because this sums up to n, this sums up to n, and so on and so forth. Plus dot dot dot. And how many ones do we have? Well, we take 1 1 and then 2 2s and then 4 4s and so on and so forth. So we are taking the summation of like 1 plus 2 plus 4 up to something, right? Such that it's less than or equal to n. But this is just 2 times k plus 1. Yeah, this is 2k plus 1 minus 1 less than or equal to n. But this is precisely just means that k is k is something log of n, right? So it's relative to logarithmic base 2 of n. So that is the reason why this harmonic series is O of n log n. But we know that, but how do we solve the problem where like for example, there are multiple ones, but n over 1 plus n over 1 plus dot 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 n over 1 n times is not O of n log n, that's pretty much n squared, right? How do we solve that? Well, there's an easy fix. You only consider the distinct values in the array A, And each time you consider them, you also consider their count. So the algorithm is just create like an array for the points, for the first n points. So it's going to be length of n. And for each frog, you want to mark how many frogs of that value a sub I will hop onto that, or will step on that point. So for example, we start the frogs here, and there are like the frogs with a hop step of 2 has a count of 3. So this is the count, this is the hop, or a sub I. Then we will mark 2 here, and then we will add 3, then we will add 3, then we will add 3, and so on and so forth. And then, for example, we have another hop. Let's say it has a hop of 3, and its count is, let's say, 2. Or let's do 2. So we start here, so it will hop 3, so we will add 2. 3, it will add 2, and then 3, we will add 2 here, so this becomes 5. So this becomes 5 here. And then in the end, okay, so all of these are initially 0 because we never hopped it before. So in the end, we will find the point that has the maximum number of like frogs that it hits, or it got hit by. And that's basically the solution. So the easy fix is to store a sub I in a dictionary and their count, and then create an array of the points from 1 to n, the possible places where the trap can be on, and you iterate over the distinct values of a sub I, and then while it can hop to a point, so the current plus the leaping power of the frog is less than or equal to n, then we hop there. So while the point is reachable, we hop there, and we increase the point by the frequency of that distinct a sub I, and then we just print the maximum element in the trap array. Right, so last two problems. So let's discuss problem G. So the problem G is basically, if you place the compass, it must point towards the morning star in one of these directions. That's basically it. So in an infinite grid or whatever, you must be able to place the compass and the morning star in such a way that the compass points towards the morning star. And you're given a set of points, and you can only place the compass and the morning star in those points. And the number of points is at least 2. So what's the solution here? So by symmetry, if you place the morning star here, and then like the compass here, and the point stars that, we can also place the morning star here and the compass here, and it will point towards the opposite direction. So there are only really 4 main like lines that we have to consider. The first line is the vertical line, the second line is the horizontal line, the third line is the diagonal that goes down, and the fourth line is the diagonal that goes upwards. And we have to determine how many points are collinear in this certain line. And notice that a point can only be in one of each type. Does that make sense? You cannot have a point that is inside of two different like diagonal that goes up lines. Like that's impossible unless those two lines are intersecting or parallel, exactly the same line. And we have to determine what are those lines that each point belongs to. The vertical line, this has an equation of like uh, x equals like a or something. This line right here has an equation of y equals b, where b is a constant, a is a constant. This line right here has an equation of um, y equals negative x plus something, some value c, let's say. And this equation has a formula of y equals x plus c, because this has a negative slope. Negative 1 is the slope, and 1 here is the slope. Now consider a point AB. What are the lines for each type that it can belong to? So for the vertical line, it will belong to x equals a. For the horizontal line, it will belong to y equals b. For the line that goes upward, it will belong to y minus x. But what is y minus x, right? That is just b minus a. Because y minus x equals some value c, right? It comes from here, right? Y minus x equals c. The point AB must satisfy this equation, so b minus a equals c. That is why y minus x equals b minus a. And for this line right here, um, similarly, it's just y plus x, which is b plus a. So these are the four lines that this point can belong to. Now consider a line, and suppose it has like k points in that line. Now how many ways can you put the compass and the morning star among these points? Well, that is precisely just the permutation of k2, which is just k times k minus 1. And this works when k is equal to 1, because it's just going to be 0. So you cannot place it at the same point, if that makes sense. I don't think you can. Yeah, at one point and the morning star at another. Okay. Um, so that's just the solution to this problem. What I did to implement this is to store the frequencies of a certain like constant, and what constant we're talking about, it's the right hand side of these equations. So for this type 1 line, how many points have this as like the constant, and how many points have this as the constant? So that's the general gist of the implementation. So you store that frequency, so you will increase um, the line that goes upward diagonally, such that the constant is yi minus xi, so you will increase that frequency. Now after we do that for all the points, um, we consider each line, um, for each type, each specific line for each type, and we increase our answer by the frequency times the frequency minus 1. And then the last problem, problem H. Okay, so I have a funny story about this problem. I actually took a lot of time solving this problem because of one main reason. I thought that my first insight was this can be represented in a graph problem because it's too complicated to be a greedy. Or although there is a greedy element in this problem in general, but like a simple array problem, I didn't think that um, this could be solved in like a weird iteration type way. So I thought a graph might work in this problem, but then I was hesitant about that because I was thinking this was a div 4 round, so I don't know if ever a div 4 round would include a problem that should be solved using graph theory. That's why I was like hesitant to try out that graph approach. So I was like trying to find some sorting or like binary search type idea or insight, but none of them worked. So I ended up using the graph theory approach, and I was able to convince and prove to myself that the graph approach or graph solution is actually correct. So what's the graph problem solution? And in these types of problems, maybe this is not um, a good tip because it might throw you off sometimes, but it's um, quite handy to consider a problem with like two positive integers n and m and like pairs of integers ai and bi for each m. Like that is like a template of a graph theory problem. That's why the first time I read this problem, I thought of graph theory, but I was hesitant for like, I don't know, 30 minutes. But yeah, so let's explain the graph approach for this problem. So let's first explain the problem. You're basically given an infinite line, and you want to place soldiers in the camp, and there are camps at each integer point. You want to place soldiers so that it satisfies m conditions. Condition I says that soldier ai should be um, d sub I in front, d sub I meters in front of where person b sub I belongs to. So if d sub I is negative, then um, a sub I should be behind b sub I. And if there's a way to do that, then you print yes, otherwise you print no. So what is this problem? So let's consider the graph theory representation of this problem. But what exactly is that like representation? So is it an undirected graph? Is it a directed graph? And surely it's a weighted graph because we have like a third value here, third quantity. So what does this look like? So let's consider this example here. So a sub I, b sub I represents a connection between a sub I with b sub I with a weight of d sub I. There is a connection from a sub I to b sub I with a weight of d sub I, and connection from b sub I to a sub I with a weight of negative d sub I. For example, 1 and 2 are connected. So from 1 to 2, there's an edge with a weight of 2, and going back, it has a weight of negative 2. So why is this important? It just represents that um, AI is, or sorry, B sub I is towards the left of A sub I, 2 meters away. And 1 is towards the left of 2, negative 2 meters away. So that's the general idea. Because suppose you place the soldiers here, you can like sort of infer from the conditions, like this must be towards the right of that, d meters apart, and this must be negative d meters apart, and this one must be negative d sub 2 meters apart and negative d2 meters apart. So that's basically the graph idea. It's a graph representation, but we can simply just um, draw it this way. So that's from 1 to 2, and then 2 and 3, um, connection with weight of 4 and then negative 4. 4, 2, there's a connection from 4 to 2 with a weight of negative 6, and 2 to 4 with a weight of 6. 5 and 4, so 5 to 4 there's 4, I think, and then 4 to 5 there's negative 4, and then 3 to 5 with a weight of 100, and 5 to 3 with a weight of negative 100. So consider a connected component of this graph. Notice that since this is technically a directed graph, but it behaves like an undirected graph, because for each pair A sub I, B sub I, there are two edges which goes from that and behind. But the idea is that in opposite directions there's also opposite weights. So this is technically not an undirected graph, and in general these graphs, even if they have the same weight, are not undirected, because they're like what do you call this? Their degrees are different, and so on and so forth. That's what we're taught. But in general, this behaves like an undirected graph. So consider a weakly connected component. It's also a strongly connected component. It's easy to prove. So we consider connected components in general. Notice that two connected components, their informations are independent from each other, which means that you can place wherever these like nodes are in the line. It will not affect these other soldiers in another connected component, because there's no restriction between them. So that means that we can literally just place like one vertex or one soldier, like choose any soldier in this connected component, place it in, let's say, 0, or in point 0, and then from then on we do some traversals such that their relative positions are correct. And notice that the only real sort of uh, sort of conditions that might be able to provide a wrong answer or an answer of a null are graphs with cycles, because when you consider a tree, right, there's only real there's only one path between any two, or forests if there are other connected components. But consider a tree. There is only one like path between any two nodes. So you're pretty much guaranteed, I think, to what do you call this? To satisfy the condition, because there's only one way, and each node is just like reliant on its parent, where it's positioned. So the only condition where this might fail is like a cycle. And in traversals in general, when we do like DFS or BFS or any other traversal, but these are the two most common, you only get a cycle if you visit a node that's already visited and you did not come from that node. That makes sense. Um, so if that's the case, then we can use one of these two. We can check a cycle, and we can use one of these two algorithms. So I chose DFS. So what I did was, again, you can just choose any soldier in this connected component. Then you can place him in, like, let's say point 0, and then use DFS from that point. So let's start from 1, we move towards 2. So it says that there must be 2 apart. So, like, let's say 1, 2, 3, 4, 5 here. So 2 must be 2 apart from 1. So it must have a distance of 2. A negative distance will mean that it's towards the left. And then let's traverse. Obviously, when we go back, right? When we go back, um, it says that from 2 to 1, it must have a distance of negative 2. Well, we already said that the distance of 2 from 1 is 2. So we're trying to check if 2 to 1 must have a distance of negative 2. Well, our current distance right now is 2 plus negative 2, so that's 0. But notice that 0, oh, I forgot to mention, we are keeping track of the current total distance of the path, or of the traversal. Now it's 0, right? So we check the distance of 1, and it's 0, so it's fine. And then we move towards the other edges. So from 2 to 3, it must have a distance of 4. So the total distance of 3 would be 6. And then from 3 to 2, it will be negative 4, but the current distance is now 2. So 3 to 2, 2 has a distance of 2, so that's okay. And then let's move towards the other vertices. For example, this one. From 2 to 4, it must have a distance of 6, so 4 must now have a weight of 8. And then that. And then let's say go from here. So 3 to 5, it has a distance of 100, so this must be, I think, 106. But then again, there's like a cycle that exists here. Those are the only conditions that might fail. So as you can see, from 4 to 5, it must have a distance of 4. But the distance from 4 to 5 is like 98 based on our calculations before. So now these conditions cannot hold at the same time. So I forgot to mention, why is this correct? Like, why is like maintaining the current distance of the traversal correct, and then checking whether the distance computed before is the same as it. And if there's no distance computed before, we just store it. So why is that algorithm correct? Well, notice that if we want a condition, these conditions to hold, then there must be like um, there must be a path. So keep in mind this is a path. So you don't visit vertices twice unless it's a cycle. So um, there must be a path from any two vertices, and that path must only have the same distance, if that makes sense. So, for example, in a number line, like going from here, then here, it must be the same as going from here to there. And since we never visit a vertex based on our algorithm, we never visit a vertex twice, then we maintain a path. So we don't actually like repeat cycles over and over again until we get like an infinite negative weight cycle or an infinite positive weight cycle. So we don't accumulate the paths. So we're guaranteed that if we go from like one to any other vertex, that path we must assume that that path weight must be their actual distance. And if there's another path that goes from 1 to 4 that has a different total distance, then that means that the conditions cannot hold at the same time. And that's pretty much the problem. You want to store the triples ABD as a graph such that there is an edge from A to B with a weight of D and an edge from B to A with a weight of negative D. Now you do a DFS traversal, and you want to keep track of the distance of a node from its representative node in that connected component, um, and whether it is already visited or not. So if it's not yet visited, we know that the distance is not yet computed before. So for each connected component, that is by checking whether the node is not yet visited, we um, traverse using DFS in the graph. So we start with any um, vertex in that connected component, and let's place that representative in point 0. Now this is our DFS function. Once we visit a node, we will set the node's distance from its representative node to be h. So we passed it out. And we visit the node u. Then we traverse um, towards the next nodes that are adjacent to u. And there are conditions to check. So if the node is not yet visited, we already know that it's not yet, the distance is not yet computed, so we can just traverse to that node already. Otherwise, it is visited, right? So else if the current distance, so this is the current distance, right? H is the current distance in our traversal, plus the weight from u to v is not equal to the distance computed before for vertex v, then our answer is false. So that's pretty much the only condition that can make the answer no. And then in the end of our program, we just output yes or no based on the value of answer. And that's pretty much it. That is Codeforces round 886. Thanks for watching, and I hope you learned something in this problem set.